Right, for this one, we have a laser going through two slits. Each has width A, and they say the pattern looks like this. So you got to look at this pattern and recognize a few things. They're showing you the diffraction envelope here in dotted lines. Right? It's one big envelope with a minimum that we really care a lot about, right there and right there. Central maximum is the width of the central maximum. Then they're showing you an interference pattern underneath it, and it's being modulated. Right? That's why the interference is dropping. And it looks like we've got one interference maximum right here, right on the minimum. Now, it looks a little confusing. You see these two bumps, and you can say, are those maximum, interference maxima? And they're not. You got to think about the spacing. They're evenly spaced. There's one here, and one here, and one here, and one should be there. Right? These are too close together. Those are the two edges of that interference maximum, and since it's cut it right in the middle, it's left two little bumps. But those are not fringes. Those are not interference maxima. So what we have here is the central peak's edge killing the m equals 3 maximum. All right, so let's move forward and see what we can get out of that. Let's see, what is the separation, which we often call, in this case, since the slit width is A, I'll call the separation D. I know that gets flipped around sometimes. A, call D, and so what we know then, we can read this pattern and tell it happened on m equals 3. So for diffraction, A sine theta equals lambda, that's the m equals 1, where the 0 is. And for interference, that would be D, because it's separation, sine theta equals 3 lambda. And they're both happening at the same angle. Right? So if I make the sine thetas the same, then lambda over A equals 3 lambda over D. So I get the separation D equals equals 3 yeah. So the D equals 3, like that. Right. All right. And part B asks, I believe, if the light with a smaller wavelength were used. If we were to use a shorter wavelength of light, how would the pattern change? You can look at both of these and say if A and D were fixed, and we made this smaller, lambda smaller, the angle has to get smaller. So if we used a shorter wavelength, both the interference pattern would contract, right? The angles, everything would get smaller, and the diffraction envelope would contract. So the whole pattern would contract. So B contracts everything. We reread part C. If the slits were made to be further apart, but have the same width, what would happen? Let's see, if the slits were further apart, if this got bigger, so same wavelength, this got bigger, this would have to get smaller. So the slits further apart also contracts the interference pattern, but this is the same, so the envelope would be the same. So that would be the interference pattern contracting, the envelope staying the same. You would get more fringes, basically. I'd answer it by saying more fringes under the central maximum. But you should probably write a little bit more if it's an example. Okay, so for part D, we're going to assume the slits are ideal. And okay, so for part D, we're going to say now, we're going to say that D equals 12 microns. And we're going to assume the slits are ideal, which basically means A equals 0. They have no width. So we're just doing an interference problem. And the question was, using small angle approximation, found the location of the m equal 5 maximum. So for part D, find y for m equals 5, because it said the location, not the angle. Assume small theta. Okay. So for that, you just say, well, D, 12 microns, I'll do it in microns, sine theta equals m equals 5 times lambda, and did they give me a lambda? Or 633 nanometer light. So that's in microns. This needs to be in microns, 0.633. And for small angles, sine theta, if we think about what that triangle will look like from the slits to the screen, there's the theta. For small angles, there's the y. And we really know usually this distance to the screen, which for this one is 2.4 meters. So the small angle approximation here is, even though we know the tangent of that angle, y over 2.4 meters, for small angles, tangent and sine are basically the same, because the cosine is about 1. So we could replace that with y over 2.4. 12 microns times y over 2.4 equals 5 times 0.633, and you get the right answer. You get y equals 0.633 meters. Y equals 0.633, well, 33 meters. All right, that's this y right here. Y for m equals 5. And then the last question is, now do that again without making a small angle approximation. So I'm going to do it up here because I've run out of room. So part E, the only difference is we can't just say that y, that sine theta, is y over 2.4. We actually solve for theta. All right, we say that sine theta is, in this case, 5 0.633 over 12, and we actually get that our theta is 15.3 degrees. Right? So we actually treated it properly like a sine. Now we know the angle, though, and we now know exactly what the tangent is. Take the tangent, 15.3 degrees, and set that equal to opposite over adjacent, y over 2.4 meters, and you solve that, and you get y equals 0.656 meters. All right, so a little bit different, 0.633, 0.656. So the small angle approximation was pretty good.